In this video, we're going to talk about approximating solutions to traveling salesperson problems. What we're doing is looking for Hamilton circuits, right, for a graph. So circuits that begin and end at the same vertex and hit every vertex exactly once. And in the past video, we looked at the brute force method. We listed all of the possible Hamilton circuits. We found some weights and then chose the optimal solution from that list as the one with the smallest weight. In this video, we want to look at two different methods for just finding an approximal solution. It's not going to be perfect, but it's going to be close enough for the purposes of the problem. So the first one of these is the nearest neighbor method. And here's how this works. We draw a complete weighted graph for the problem. We start at the designated vertex. So if we're told, begin and end at a certain destination, start there. Then we pick the edge with the smallest weight and move to the second vertex. Right? Then at the next vertex, you pick the edge with the smallest weight that doesn't go to a vertex already used. If the weights of the two edges are the same, right, in any of these cases, you pick either one, and you just continue until the circuit is complete. Alright, so you start at a vertex, look at your options for going to the next vertex, pick the smallest one, and you just keep going, always choosing the smallest one. Okay, so here's an example. A regional manager decides that she needs to visit all of the company locations in her region during the last 2 weeks of May. She lives in City A and needs to visit all of cities B, C, D, and E, and then return home. The driving time in minutes between the cities is shown. Use the nearest neighbor method to find the route that will give her the least amount of driving time. Alright, so we'll start in City A, and then I'm going to start making a list of the vertices in order as we go. Okay, so starting at A, choose the edge from A that has the smallest weight. Okay, so our options are 200 if we go to B, or 415 going to C, 390 going to D, or 240 going to E. So the smallest one is definitely the 200 going to B. And I'm also going to trace or highlight these, and that way we don't repeat an edge that's already used. That's part of the algorithm. At B, I have a choice of 310, 510, and 350. So we choose 310 and go to C. At C, I can choose 415, 410, and 425. So we'll do 410 and go to E. And then from E, we have 240, 350, and 375, and 240 is the smallest. Okay. You can also see at that point that we've covered all of the vertices, and we just need to go back to the original destination. And so notice, that's the other part of this algorithm. Okay, we want to pick the edge with the smallest weight that doesn't go to a vertex already used. So even in this case, like let's say that this 375 had been a 200. Oops. Hold on a second, that's not quite right. I haven't used all of the vertices. Okay, so I can't go back to A. Okay, because I've missed D. So in this case, I do want to choose this 375, because if I went with the smallest weight, I would end up at A or B, which I've already used. Okay, so go to D next. And now we've used all of the vertices, so now my previous comment works. Alright, so now, regardless of the smallest weight, I just need to return to the starting location. So I'm going to go back to vertex A at that point. Okay, and then to find the approximation for the optimal solution, we have to add up all of these weights. Alright, so add 200, 310, 410, 375, and 390. And this gives an approximation of 1685. Okay, that would be the minutes of driving time. Now, if you're really interested in this, You could try this using the brute force method and see if this actually is the optimal route, or if there is a smaller optimal route. Okay, so there are 5 vertices, so you'd have to list out 24 Hamilton circuits, go through and find all of the different weights, and see if there's one that's smaller than this. Alright, you could also just try adding some different numbers. Okay, so choose some random Hamilton circuits out of that list of 24, and just see if you happen to hit on one that is a smaller weight. Alright, this method is fairly efficient, and you can see it was pretty easy to do, but this isn't guaranteed to find the true optimal solution. So one graph theory question was, are there other approximation methods? Can we find a better solution? So in the quest to find different approximation methods, we ended up with one called the cheapest link algorithm. So all of these are just giving us different options to use, and then depending on the context and of the situation and what type of solution we're interested in, we might actually use any of these methods. So the cheapest link algorithm, instead of choosing adjacent edges to form the path, just pieces it together from all over the graph, and then we use some different requirements to make sure that it does become an actual connected Hamilton circuit at the end. Alright, so nearest neighbor, we started somewhere, and then we only just chugged along from that vertex to other vertices, alright, and then all the way back to the beginning at some point. Alright, etc. Cheapest link, we might just pull different edges from all over the graph, okay, and then eventually we're going to start to connect these, okay, and they'll turn into a Hamilton circuit. Okay, so here's how it works. So you draw the complete weighted graph, pick the edge with the smallest overall weight. Okay, so you're going to just look at the entire graph and look for the very smallest one. Okay, it does not have to be the one that connects to the starting destination right away. If you have a choice between 2 with the same weight, then you can choose either one. Okay. And then you just go on and you keep picking the next cheapest edge, but to make sure that we end up with a Hamilton circuit, we have to make sure that whatever we choose doesn't enclose a smaller circuit that doesn't reach every vertex. Right? So if we chose something and we ended up with this little circuit, and we ended up with other vertices we hadn't hit yet, that's a problem. And we also have to make sure that it doesn't result in 3 chosen edges coming from the same vertex. Okay, so let's say I chose these 3. Right, well, that's a problem. And the reason is that we just want to hit every vertex exactly once, right, except for that beginning one where we're going to end up at the same spot. Right, so you can kind of see, like, if we're going along our circuit here, if we come into one vertex and then leave it, well, then this third edge means that I'm hitting that vertex a third time, or a second time. Okay, so I'd be passing through it once, but then I would have to hit it again with that edge, and that's not what we want for a Hamilton circuit. We just want to hit the vertices once. Alright, so we're just going to keep picking the next cheapest edge, make sure we don't run into those 2 sticky situations. Okay, no smaller circuits, no 3 edges out of one vertex. Alright, let's try it out. Use the cheapest link algorithm to solve the problem from example 5. So this is the one that we just did, okay, using the other method. Alright, so I would scan the whole graph, look for the very smallest weight, and I see a 200 between A and B. That looks like the smallest. Okay, and then I look for the next smallest. Alright, so scanning, I see a 240. And if I choose that, I haven't made a smaller circuit, and I haven't created 3 edges out of a vertex, so that's okay to pick. Alright, the next smallest I see would be this 310. And same thing, no smaller circuits, no 3 edges out of a vertex, so I can choose that. And then I see a 350. Now here's a problem if I choose that one. If I do, I would end up with this little circuit that goes between A, B, and E. Okay, but I haven't hit vertex D yet, so I can't do that one. Okay, so I'm going to cross that out for now and move on. After 350, we have a 375, and I can choose that. Alright. Then we have, let's see, I think we've hit all the vertices, right? So we just need to complete the circuit. Okay. Now let's keep going along here and we'll find the next smallest weight. Okay, so next would be let's see, we have a 390, but same problem, that's going to create this little circuit between A, D, and E. I don't want that, so I can't choose that. Okay. The next smallest I think would be 410. Same problem, we've got this circuit that we don't want. And also the problem there, we'd have 3 edges coming out of vertex E. That was another situation to avoid. Okay, so I can't choose that one. So then I'm down to 415, 425, and 510. Okay, this makes another circuit that I don't want. 510 makes 3 vertices, or 3 edges coming out of vertex B, so I can't choose that one. Okay, and then the algorithm has led us to what you probably saw was going to be the last edge we picked. That's this 425 connecting to C. Okay, so I do want to emphasize, even though the very first edge I picked did connect to vertex A, which was our starting point, it did not have to. If the 200 had been over here, then I would have chosen that edge first, even though it was not at all connected to vertex A. Okay, so let's add up these weights and see if you end up with a solution that's more optimal or less optimal than that nearest neighbor method that we already tried. Alright, so the sum of these is 1550. Right, and if we go back and look at the nearest neighbor method, in that case our optimal approximation was 1685. So this definitely ends up with a more optimal solution. And then same thing, even though we found 2 good approximations, this one's a little bit better. We don't know for sure that this is the optimal solution. We'd have to use the brute force method to test all of the Hamilton circuits, just to make sure that there isn't one that's better than this. Okay, so that concludes this section on Hamilton paths and circuits, and you have 3 options for finding them. You've got the brute force method to give an exact solution, and then if that's too time consuming, we have 2 others to approximate. We have the nearest neighbor method and the cheapest link algorithm.